Ionic bonding has a naming technique that's very different from covalent compounds. The first set that we'll be looking at deal with binary ionic compounds, which means only two elements are involved. That should mean one metal with one nonmetal. And in this particular set of examples, we have a fixed oxidation state, which means the metal can only have one possible oxidation state, or one charge, on the periodic table. These are generally in groups 1 and 2. Those are your alkaline metals and your alkaline earth metals. The elements in the transition metal region typically have more than one oxidation state and will be treated in a later video clip. When we go to handle the nonmetal, for the most part we will be using the top oxidation state listed in the box on the periodic table. And by top, I literally mean the one furthest in the upper part of the box. Not the highest value, not the smallest value, but the one at the top of the box for that element. Your steps for writing formulas are as follows. First, you write down the element's symbols. Metal comes first, followed by nonmetal. Remember, the first letter is capital, and the second letters have to be lowercase for each element. So there should be 2 capital letters in your formula. Next, you want to write down the oxidation states that you're picking as charges up on the top right of each of those elements. It's the exponent. We will be crisscrossing them. It's going to look like an X when I show you this on the next slide. You will not be carrying the sign forward when you crisscross. What this is doing is making sure that we have a neutral compound. The number of positives will always cancel out with the total number of the negative charges. In the end, we want to simplify these numbers if they have a common factor. So 2 and 4 would simplify down to 1 and 2, or 2 and 2 simplifies to 1 and 1. There's a single exception to know, and that involves the mercury 1 ion. Mercury with a +2 on the top and a little 2 on the bottom is listed as dimercury on table E. It never gets simplified. So as we deal with this a little bit later, do not simplify mercury with a +2 and a little 2 at the bottom. Okay, we will walk through a couple of examples, and then I'll show you some work on additional ones. Okay, calcium oxide. Your first step is to look up calcium and oxygen on your periodic table. Calcium's oxidation state is +2. Oxygen's is -2. Please take a moment to pause this and confirm that you can find that on the table. When we crisscross, what is happening is oxygen's 2 is coming down to the bottom right of calcium, and calcium's 2 is coming down to the bottom of oxygen. So you see how the yellows and green have crisscrossed and become little subscripts. That's telling you how many calciums and how many oxygens are in your formula. The last step that we want to look at is to simplify or reduce it if possible. And both of these have 2 as their subscripts. So we can eliminate the 2 and show the simplest ratio, which is CaO, calcium oxide. This is an empirical formula because it's in the simplest ratio. All ionic compounds will show empirical formulas because the atoms or ions exist in a large crystal where there's an awful lot of each of the positive and negative ions. They don't exist in individual molecules, so the empirical formula shows you the simplest ratio of the elements involved. The second example will be sodium nitride. Sodium and nitrogen are involved, so we look up sodium and nitrogen's oxidation states. Sodium is +1, and for nitrogen there are several choices. We take the top value, which is -3. When we go to crisscross the charges, the 1 comes down to the bottom of the nitrogen, and the 3 comes down to the bottom of the sodium. Notice how the minus sign does not follow because we can't have minus numbers of sodium in a compound. To simplify this, they are already in the smallest ratio. However, we don't typically write 1s at the bottom. So we show it as Na3N.